Hello once again, phenomenal people. Of course, you know who it is. It's Matufari here, and welcome back to my space. So far in this playlist, we've been able to successfully compute the 5 limits in the problem set without using L'Hopital's rule or series expansion. And I've decided to add a bonus video where we also look at another limit question without using L'Hopital's rule. But this time around, it's a question that does not involve trigonometry at all. Also, there was a mention of a particular limit at the beginning of the playlist where we said we would come back to using L'Hopital's rule. So I intend to do that, and also quick in a very fast pace go over all the questions showing how we could have actually done them using the L'Hopital's rule. So going over the things we need to do, it's probably going to be a relatively longer video than the ones we've seen in this playlist so far. Let's get into it straight away without wasting any more further time. All right, the first question is the limit of x. It's a very popular question, and many students they do this using the L'Hopital's rule directly. It's not wrong. L'Hopital's rule is actually not wrong, but according to what we discussed in the motivation, we know that it is actually a topic that comes after differentiation. So for a course where you've not been taught differentiation yet, and you're giving questions on limits, the lecturer is expecting that you solve those questions without using L'Hopital's rule. So it's a good trick to have in the back to be able to solve questions without use of L'Hopital's rule. So how do we actually solve this particular question? The answer is factorization. So ordinarily, we know that if we have limit as x goes to 2 of x squared minus 4 over x minus 2. It's the same thing here. For both of them, if we go with direct substitution, we get a raised to power n minus a raised to power n over a minus a, which is 0 over 0. And in this case, we have 2 raised to power 2 minus 4 over 2 minus 2, which is also 0 over 0. The one on the right, how do we solve it? We factorize the numerator as 2 squared x minus 2 x plus 2 over x minus 2, such that the x minus 2 cancels out, and we now have the limit as x approaches 2 of x plus 2, which is equals to 2 plus 2, and that is 4. The same idea is what we're going to use for the question we have at hand here. But for us to be able to do that, we need to be able to factorize x raised to power n minus a raised to power n. And how do we do that? So first and foremost, we observe that there is a pattern. For difference of 2 squared, x squared minus a squared is equals to x minus a, x plus a. And I put it to you that x cubed minus a cubed is actually also equal to x minus a into bracket x squared plus ax plus a squared. So we could show this by doing the long division. So if we divide x cubed minus a cubed by x minus a, what is going to be our quotient? So x goes in x cubed, we have x squared. And when we multiply x squared by x minus a, we get x cubed minus ax squared. So the long division, the next step is for us to do subtraction. So this cancels this, and we are left with ax squared minus a cubed. And the next thing is to say x in ax squared, that is plus ax. And if we multiply ax by x minus a, we get ax squared minus a squared x. So x in ax squared will give us, have I made any mistake? X in ax squared we give us, we have to subtract this, and we'll be left with a squared x minus a cubed. So x in a squared x now. So we have plus a squared, and a squared times x minus a gives us a squared x minus a cubed, and that's 0. So it means this is the quotient, and that's what we have here. So even if we want to do the next one, x raised to power 4 minus a raised to power 4, we're going to get x minus a and x squared, x cubed this time around, plus a x squared plus a squared x plus a cubed. So as you can see, the powers of x is decreasing from 3 to 0, and the powers of a is increasing from 0 to 3. There are no other coefficients apart from 1, and they are all positive. So if we want to generalize that, we have x raised to power n minus a raised to power n is equal to x minus a, then x raised to power n minus 1. In fact, let's write it out on a bigger space. X raised to power n minus a raised to power n is equal to x minus a, x raised to power n minus 1 plus a times x raised to power n minus 2. Let's write one more. A squared times x raised to power n minus 3. Then it goes on like that until let's move this out of the way. It goes on like that, plus dot dot dot, plus the last one, which is going to be, or before the last one we could have a raised to power n minus 2x before we now have plus a raised to power, a raised to power, yes, so it should be a raised to power n minus 2, and the last one will be a raised to power n minus 1. Yeah, that's correct. So, and the thing to notice is that for each term, two things to notice. For each term, the sum of the exponents is always going to be n minus 1. So n minus 1, then 1 plus n minus 2 will give us n minus 1. 2 plus n minus 3 will give us n minus 1. N minus 2 plus 1 will give us n minus 1. We have n minus 1. Then also, if you look at the difference of two squares, for square, there are 2 terms. For the difference of 2 cubes, there are 3 terms. For the difference of powers of 4, there are 4 terms. So it means for x raised to power n minus a raised to power n, there are going to be n summands in this factorization. So it's an important thing to take note of. So let us now come back to the question. If we have limit as x approaches a of x raised to power n minus a raised to power n over x minus a, we can write this as the limit as x approaches a of x minus a using the factorization that we have up there. X raised to power n minus 1 plus a raised to power x raised to power n, a times x raised to power n minus 2 up to the last one, which is a raised to power n minus 1, all over x minus a. Then the x minus a's can now cancel out, and we can have the limit as x tends to a of x raised to power n minus 1 plus a x raised to power n minus 2 plus dot 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 plus a raised to power n minus 1. And from what we said here, there are n of them. So if we plug in a directly now, we have a raised to power n minus 1 plus a times a raised to power n minus 2 plus up to a raised to power n minus 1. For each of them, we are going to have a raised to power n minus 1 plus a raised to power n minus 1 up to a raised to power n minus 1. And because there are n of them, when you add something together n times, you get n times a raised to power n minus 1. So we have that the limit as x approaches a of x raised to power n minus a raised to power n over x minus a is equals to n a raised to power n minus 1. Okay, so that brings us to the end of the computation of limits without using L'Hopital's rule. So we are now going to roll it back and try to solve many questions actually using the L'Hopital's rule. So first and foremost, we remind ourselves what the L'Hopital's rule is. L'Hopital's rule is saying that, let me write it here. So L'Hopital's rule is saying that if we have the limit of f of x over g of x as x approaches a to be equals to 0 over 0 or infinity over infinity, then we can do the limit of x raised to power a of f of x over g of x is the same thing as the limit as x approaches a of f prime of x over g prime of x, which is actually f prime of a over g prime of a. So and when I say f prime is the derivative of f of x, and if this one will also give us 0 over 0, we go again, we compute the derivatives separately. So ordinarily, when we have a fraction f of x over g of x, the way to take as a rational function on its own, the way to take the derivative is to use quotient rule. But when dealing with L'Hopital's rule, we take the derivatives independently. Okay, so now the first one here is this guy. Copy. Let's see. So how do we do this? So first and foremost, direct substitution, we have 3 raised to power 0 minus 2 raised to power 0. So we must always test to see if it satisfies the requirements for L'Hopital's rule before actually going ahead to use it. So 0 squared minus 0, this is 1 minus 1 over 0 minus 0, which is 0 over 0. So we can use L'Hopital's rule. That means the limit as x approaches 0 of 3 raised to power x minus 2 raised to power x over x squared minus x is equals to the limit as x approaches 0 of the derivative of 3 raised to power x minus 2 raised to power x over the derivative of x squared minus x. And that is the limit as x approaches 0 of, so generally if y is equal to a raised to power x, the y dx is equals to a raised to power x natural log of a. So the derivative of 3 raised to power x is 3 raised to power x natural log of 3 minus the derivative of 2 raised to power x is 2 raised to power x natural log of 2. So it's different from, this is an exponential function, it's different from the power function x raised to power a, where a is a constant, possibly preferably an integer or even a rational number will work. So the y dx here is equal to a x raised to power a minus 1. So there are two different things. This one is exponential function, and this one is the power function. So one of the common mistakes is people mix them up. All right, so these over the derivative of this is 2x minus 1. Now, because the derivative of x squared is 2x and the derivative of x is 1. Now, let us now plug in 0. So that will be 3 raised to power 0 natural log of 3 minus 2 raised to power 0 natural log of 2 all over 2 times 0 minus 1. And this is equals to 1 times natural log of 3 minus 1 times natural log of 2 over 0 minus 1. And that is same thing as natural log of 2 minus natural log of 3, because the negative sign in the denominator here will affect the order of the subtraction in the numerator. And the answer is natural log of 2 over 3 using the laws of logarithm. Log A minus log B is equals to natural log of A over B. So, sorry, logarithm over B. And that is the answer to this limit question. So very quickly, let us now attack these limit questions one by one. Let me copy everything that we have here. Copy and have them here. So now we want to use L'Hopital's rule. So I'm going to delete the instruction there. Then I'm going to move these up. Then start picking them one by one. Copy, no. Copy, paste. So the first one, we have already seen that direct substitution will give us 0 over 0. So that gives us the license to use L'Hopital's rule. So using L'Hopital's rule, that will be the limit as x approaches 0 of the differentiation of 1 minus cosine of pi x over the derivative of x squared. And what will this give us? This will give us the limit as x approaches 0. So the derivative of 1 is 0. The derivative of cos pi x is negative pi cos pi x. And because there is a negative sign here, we get pi sine of pi x. So we have used chain rule there. So the derivative, if y is equals to cos ax, the y dx is equal to negative a sine ax. Then over the derivative of x squared is 2x. If we plug in 0 directly here, we're still going to get 0 over 0, because sine 0 is 0 and 2 times 0 is 0. So we can use L'Hopital's rule again, and that is the limit. This is equal to the limit as s goes to 0 of the derivative of pi sine pi x over the derivative of 2x. So this is equal to the limit. You can see I have never forgotten to drag along the limit expression. Until I make substitutions, I cannot drop them. So limit as x approaches 0 of, so the derivative of sine pi x, just like we did for cos ax, is going to be pi cos pi x. And because there is already a pi outside, a lot of pi's, pi squared cos pi x, and the derivative of 2x is 2. So if we do the direct substitution now, we get pi squared times cos 0 over 2, and cos 0 is equal to 1, so this is equal to pi squared over 2. Good. The next question. So of course this agrees with the answer we had initially. The next question, let's quickly copy that. Copy, paste. So direct substitution again will give us 0 over 0. We have already seen that before, so I'm not going to do that again. So using L'Hopital's rule, so this is the limit as x goes to pi of the derivative of, so in subsequent questions I'll skip this step and just go ahead with the derivative over the derivative of x minus pi squared, and this is equal to the derivative of 1 is 0 and the derivative of cos x is negative sine x. So we have negative sine x over the derivative of x minus pi squared is 2, using chain rule, 2 times x minus pi. If we plug in 0 directly here, we are going to get sine, if you plug in pi, you're still going to get sine pi, and we know that the sine of any multiple of pi is 0. So sine pi is itself, it's 0, and pi minus pi is 0, so that is 0 over 0. We can use L'Hopital's rule again, and that is the limit as x approaches pi. We differentiate negative of sine x, we get negative of cosine of x over the derivative of 2x minus 2 pi is just 2, so over 2. And if we plug in pi directly now, we have this is equal to negative of cosine of pi over 2, and since cosine of pi is negative 1, we have negative of negative 1 over 2, which is equal to 1 over 2. That, I believe, corresponds to what we have here initially. So that's correct. The next question, this copy, paste. Again, we have seen that it is equal to 0 over 0. So we just go ahead with L'Hopital's rule. L'Hopital's rule. And that means this is equal to the limit as x goes to infinity, as x goes to pi. Then we have to differentiate both the numerator and the denominator. The differentiation of the denominator is straightforward, that is cos x. But for the numerator, we have to use product rule for this term. This other term is a constant, so its derivative is 0. So if this is our u and this is our v, we know product rule says it is u dv dx, uv prime, plus v du dx, u prime v. So the first one is x times the derivative of cos x, that is x times minus sine x, so that is minus x sine x, plus the second one is the derivative of x, which is 1, times cos x, so we have times cos x. Then if we plug in pi now, what do we get? So that will be minus pi times sine pi plus cosine of pi, which is equal over cosine of pi, which is equal to, we know that sine pi is 0, so this is 0, plus cos pi is negative 1 over cos pi, which is negative 1. That is negative 1 over negative 1, which is equal to 1. Yes, I think that is what we got in the first place as well. Good. Number 4. Copy, paste. Again, initial direct substitution will give us 0 over 0, and we can go ahead with the L'Hopital's rule, and this is equal to the limit as x goes to 0 of, thankfully we have seen the derivative of the denominator in the previous question, that is cos x minus x sine x. And for the denominator and numerator, the differentiation of tan x is secant squared x, and the differentiation of sine x is cos x. Now if we plug in 0, we have secant squared 0 minus cos 0 over cos 0 minus 0 sine 0. So since sec 0 is 1 over cos 0, and cos 0 is 1, so secant square 0 is going to be 1. So this is 1 minus cos 0 is 1 over cos 0 is 1 minus 0 times anything is 0. So this is 0 over 1, and 0 over 1 is 0. That's not a problem. It's not a crime to have 0 as a solution in limits. So it's a real number. So that is also correct, which is what we got initially. And the final question, hopefully, I don't think that small space can contain it, because it's looking like we are going to need to use the L'Hopital's rule multiple times. So I'm going to need a space. So let's add a space. Good. So this direct substitution, sine 0 minus tan 0 is 0 over 0 cubed. So we can go ahead and use L'Hopital's rule. So this is equal to the limit as x goes to 0 of, so the differentiation of sine 5x. Again, let's remind ourselves, if y equals to sine ax, the derivative of that is a cos ax. If y is equals to cos ax, the derivative is negative a sine ax. And if y equals to tan ax, the derivative is a sec squared ax. So in this case, sine 5x. So all of these are just results of the chain rule. So this sine 5x, we get 5 cosine of 5x. The derivative of tan 5x is 5 sec squared 5x over the derivative of x cubed is 3x squared. 5 is common there, so I can write this as 5 over 3, the limit as x goes to 0 of cosine of 5x minus secant squared of 5x all over x squared. If we plug in 0 here, we get, let me just do this, we get cosine of 0 minus secant squared of 0 over 0 squared. That is 1 minus 1 over 0, which is 0 over 0. So that's another grounds for using L'Hopital's rule. We have 5 over 3, and the limit as x approaches 0, the denominator, the derivative of the denominator is 2x, and derivative of the numerator, we have negative 5 sine 5x. So what's the derivative of sec squared 5x? Let's do it somewhere here. Y equals to sec squared 5x. This is the same thing as sec 5x raised to power 2. So using chain rule, y prime equals to 2 sec 5x raised to power 1, then times, what's the derivative of sec 5x? So maybe I should also add it here. If y equals to sec ax, the y dx is equal to a sec x tan x. So tan sec ax tan ax. Also chain rule. So this will be 5 sec 5x tan 5x. Altogether, that will be 10 sec squared 5x tan 5x. So this is the result that we are going to use in that L'Hopital's rule. So I'm taking this, copy, paste. So let's remove the minus. All right. And in this case, I can factor out 5 and 2. So we have, this is equal to negative 25 over 6. Negative 25 over 6. And that will be sine, limit as x approaches 0, of sine 5x minus 2 secant squared 5x tan 5x. I actually believe the other method without the L'Hopital's rule is even better than this one. So this is now, again, if we put in 0, we get 0 in this part. We also get 0 because tan 0 is 0 and over 0. So this is 0 over 0, which means we can use L'Hopital's rule again. So this is minus 25 over 6, the limit as x goes to 0 of the derivative of x is 1. Thank God. The derivative of I'm going to see if I've not made any mistake. 3x squared. Okay, 2x. Alright, I think we're on the right track. Derivative of sine 5x is 5 cosine of, let's write it better, 1. So we have 5 cosine of 5x. Now we have something on our hands. So sec squared 5x tan 5x. How do we find the derivative of that? So let's come here. So can we actually write it? So this is 1 over cos squared 5x times sine 5x over cos 5x. So that is the same thing as sine 5x over, which one will be better, to use quotient rule or to use product rule? Sine 5x over cos cubed 5x, which one will be better? So let's use quotient rule. So uv, and we know that the y dx is equals to v du dx minus u dv dx all over v squared. So this is equal to v is cos cubed 5x and du dx. So if u is equals to sine 5x, du dx is equal to 5 cos 5x. And if v is equals to cos cubed 5x, the v dx, because this is cos 5x raised to power 3, that is going to be 3 cos 5x squared times the derivative of cos 5x, which is minus 5 sine 5x, and this gives us altogether minus 15 cos 5x squared sine 5x. So here we have cos cubed 5x as our v, and the u dx is 5 cos 5x, so times 5 cos 5x minus u dv dx. U is sine 5x times this ugly looking expression, so that'll be plus 15 cos squared 5x sine squared 5x. So if we multiply u, which is sine 5x, by this, we get cos square 5x sine square 5x, and because there is a negative sign there, that goes. Everything over v squared, which is going to be cosine cubed 5x times cosine cubed 5x. And so actually, so cos square 5x is common in the numerator, so we are left with, if I bring it out, we have cos squared 5x. Then this should be left with 5 cos squared 5x plus 3 sine squared 5x. Oh, sorry, we did not factor out, so I should factor out 5, so that the 5 will go here. So that will be cos squared 5x, then plus, if I factor out 5 from here, I'll be left with 3 sine squared 5x. Everything over cos raised to power 6 5x. So this will be 5 into bracket cos squared 5x plus sine squared 5x plus 2 sine squared 5x all over cos raised to power 4 5x. And this guy will give us 1, Pythagorean identity. So we have 1 plus 2 sine squared 5x over cos raised to power 4 5x. That's beautiful, because we also know that 1 plus 2 sine squared theta. So what is cos 2 theta? Cos 2 theta is equal to 1 minus 2 sine squared theta. So it means that 2 sine squared theta is equal to cos 2 theta minus 1. Then it means that 2 sine squared 5x is equal to cos 5 times 2x, which is 10x minus 1. Will that actually help us? I don't think it will. You know what? I'm just going to use these directly. You know what? I think I'll just rather, instead of trying to simplify that, I think it's better I just write this as equal to 1 plus 2 sine squared 5x sec raised to power 4 5x. Yeah, that should work for our purposes. So this is the derivative of this guy. So I'll paste it here. I was bigger than what is here. Then we still have a 2 somewhere there. So 2 times 5 will be 10. Then should this really be negative? So we factored out a negative 5. That should be positive. This should be positive. Good. Whew. That was long. And this is now equal to, I can factor out a 5 again. 5 times 125. 5 times 25 is 125. So before I do that, let me clean up this mess. This should be here. All right. So 5 times 25 is, so we have negative 125 over 6, the limit as x goes to 0 of cosine of 5x plus 2 times 1 plus 2 sine squared 5x times sec raised to power 4 5x. Then we now apply the limits now, direct substitution. So that's 120 minus 125 over 6 times cos 0 plus 2 times 1 plus 2 times sine square 0. This is just formality. Ordinarily, I wouldn't do all this in a solution. So this will be sec raised to power 4 0. And that is negative 125 over 6. 1 plus 2. 2 times sine square 0 is just 0. So 1 plus 0 is 1. Then sec raised to power 4 0 is 1 raised to power 4, which is 1. That's minus 125 over 6. That's 1 plus 2, which is 3. And our final answer is negative 125 over 2. Finally. I didn't expect this video to be that long. But yes, we've come to the end of the series. The playlist. We've seen how to actually solve these questions without using L'Hopital's rule, except of course this special one, which there is nothing we can do about it without using the L'Hopital's rule. And I hope you've gained one or two things and you've learned one or two tricks to use. And if there are still anything that are unclear, do well to leave your questions in the comment section below. And we'll see in the next playlist or in another time. Till then, may the mathematical force be with you. Chill. Bye.